All right, our next talk is by David Spivak, who's going to tell us about poly, an abundant categorical setting for mode-dependent dynamics. Let me just say for anybody who might be joining us that if you have questions, you can keep them until the end when we'll have a few minutes, or if they're urgent and short, you can speak up or ask them in the chat for anyone else who might be able to help. So take it away, David.
Great. Thanks, Mike. Yeah, so this will be a talk about poly, and by abundant, I just mean I love you, poly, are my favorite category. Okay, so let's see if I can actually scroll slides. Yep. Okay, so since I was a kid, I thought that math could help me think about regular life, like this thing that's happening right now where I'm talking to you on Zoom, and there's maybe you're trying to get something out of this, and what does it mean to get things out of it? Kind of in the Toby Cyber Kittens direction, like how do we actually do this stuff? Isn't there, if we can say things precisely about it, shouldn't we be able to say it mathematically? So at some point in my life, I kind of like overdo things a little sometimes. So at some point I thought maybe everything in the world is information, and that's all it is. It's just information. And we just need to understand what information is. And well, how would we start on that? Well, maybe we should see how people store information and transfer information. And it's stored in databases and it's communicated through queries and what's called data migration. I thought a lot about that. And then I thought, well, but when I tried to get process and recipe and things like that into this database and information world, I had a real hard time making it fit well. Somehow the database queries weren't helping me understand the process as it transformed. And so I started thinking, okay, maybe everything's process and everything's just, there's this interactive transforming of each other's products into new things. How are complex processes formed out of simpler ones? And in the shocking plot twist, these two worlds converge in a single category called poly. That doesn't mean it subsumes all of it, but it has some really interesting aspects of both. And I'll only have time to talk about the dynamics today, but it also has this whole database side to it. Okay, so I'm going to recall some basics of this category. I'll talk about how it models mode-dependent dynamical systems, and then I'll just conclude with a brief summary. So what I'll call poly has many names. So for experts, it's the free, completely distributive category on one object. If you have dependent sums and products and you can move products past sums, then that's called this completely distributive. It's the full subcategory of the functors from set to set, spanned by those that preserve connected limits. So like equalizers and fullbacks. It's the full subcategory of all those functors from set to set spanned by the coproducts of representables, and that's one we'll be using the most, but I'll go into it in a second. It's also, David talked about this generalized, David Jasmyers talked about this generalized lens category, and so did Toby. Basically, if you take the category of sets and you take the self-indexing, you take this the construction of the pointwise opposite, you get poly again. And it's also called the category of containers in the sense of Michael Abbott. But I want to make this a lot easier. And just looking at that polynomial there, y squared plus 3y plus 2, all of the polynomials I talk about today will just be in one variable, y. And if you see any other letters, those will be constants. And there'll be constants corresponding to sets. So that 2 there is a set with 2 elements. The 3 is a set with 3 elements, etc. And so y squared plus 3y plus 2, which is y plus 1 times y plus 2, is a polynomial in the very sense you're used to. David talked about bundles. And in the sense of bundles, this would be the bundle shown there. It's got 6 things on the bottom because there are 6 summands, y squared, y to the 0, y to the 0. And the fiber over each of those 6 is the exponent. So there's 1 with 2, 3 with 1, and 2 with 0. And then on the right-hand side, there's this corolla forest, basically a bunch of trees with height 1. And that's only interesting when we start talking about composition of polynomials where the trees would start to grow. But I probably won't draw that again. One reason I drew it here is because the way I'm going to talk about polynomials is in terms of what I call positions and directions. So there are 6 positions here, and the first position has 2 directions to go, this is kind of in the same flavor as David was talking about, which like the kind of tangent space of that first position is two next directions, whereas for the next three, it's one. And then the last two, they're kind of done with zero directions. Okay, so category, theoretically, the easiest description of poly is that it's sums of representable functors from set to set. So for any set S, let y to the power S denote the functor that takes a set S and returns the set of functors from S to anything. Sorry, it takes any set and returns a set of functions from S to that set. That's called the functor represented by S. You might, it stands for, the Y there stands for Yoneda, because this is the Yoneda embedding where that S is functorial in S. And so a polynomial is a sum of these representable functors. So it's a sum over some indexing set I of a notation I'm going to use is y to the pi. So a morphism of polynomials is just a natural transformation. And in poly, plus is the coproduct and times is the product. So y squared plus 3y plus 2 really is the product of y plus 1 and y plus 2. And just for notation, again, I'm going to write polynomials this way, that note that if you plug 1 in for y, every one of those summands turns into 1, whether p is 0 or 1 or 2, pi is 0, 1, or 2. So I is p of 1. That indexing set I is p of 1. So I can just write the polynomial as the sum over elements of the set p of 1 of the representable y to the pi. That's notation I'll use throughout the talk. There's been a lot of talk about lenses, and a lens, the objects in this category called lens are pairs of sets, ST, and a morphism from S1T1 to S2T2 is a function from S1 to S2 and from S1 times T2 to T1. But that, it turns out that the category of lenses is equivalent to the category of polynomial, just the monomial polynomials. So if you have a monomial sy to the t, that would correspond to the lens s comma t. All the polynomial maps from s1 y to the t1 to s2 y to the t2 would be exactly the get put situation you saw in 1 up there, the set of all lenses from s1 t1 to s2 t2. So we can think of poly as a generalized lens category. It's like the category of lenses, bimorphic lenses, that a bunch of people have talked about today, Mario and Toby and many others. But the objects are more general. Instead of just monomials, it's any polynomial. We've seen 2 monoidal structures on poly already. There's plus and times, but there's also 2 more. One is called Dirichlet product, whose unit is the identity functor y. And I just want to compare it with the product monoidal structure. So if you take 2 polynomials, the sum over I and p1 y to the pi and the sum of j and q1 y to the qj, and you multiply them as polynomials like you did in high school, you would get the sum over these 2 I and p1, j and q1 of y to the sum of exponents. Basically because y to the p1 times y to the q, pi to y to the qj is y to the pi plus qj. The tensor product is almost exactly the same formula, except you multiply the exponents. And the most interesting product, monoidal product, is the composition product, or substitution product, where you compose 2 polynomials. You just compose them as functors, or you compose them as polynomial functions, and it's a non-symmetric monoidal structure, which I don't personally, I mean, I see, of course, you see that in exactly the situation of like the full subcategory of cat spanned by an object, and that's kind of what we're seeing here. But anyway, it's non-symmetric, and it's a very interesting monoidal structure, as we'll see. I want to talk about that monoidal structure. Like, how do you actually, what is P composed Q? P composed Q is the sum over I in P of 1. So it's a choice of position in P. And then for every direction there in P, it's a choice of position in Q. And for every direction in Q, in that position, it's a future. And that's a kind of weird way of talking about it, but by a future, I mean, it's an element of some predefined, of some undefined set you don't know yet. So someone's going to plug in a set for that Y there, and you're required to give them an element of that set. And so we're going to think about P composed with itself n times. what is it? It's a choice of position P, and for every direction in that position, it's a choice of position in P, and for every direction there, you keep going, and then eventually, after you do that n times, you just give the future. So it's like a length n strategy where you choose a position, and then whatever they do, whatever direction they choose, you choose a new position n times. So now I'm going to talk about how this looks in dynamical system language. So a Moore machine is defined as follows. Given two sets A and B, A will be the input and B will be the output. An AB Moore machine consists of a set S, where you'll call the element state, a function R that takes a state and gives you an output called the readout, and a function U that takes a state and an input and gives you a state, and that'll be called the update function. It's initialized if it's also equipped with an element of S called the initial state. So how does this give you a dynamical system? An AB Moore machine is a kind of what you could call a stream transducer. It just takes a stream of A's, the input alphabet, and gives you a stream of B's. So how does it work? Given a stream of A's, you could let the n plus first state be the update of the nth state with the nth input, and let the nth output be the readout. And you've just gotten a stream of B's. Great. So a Moore machine consists of these two things, a function from S to B and a function from S times A to S. And that's just a lens SS to BA. Or it's a map of polynomials, sy to the S to by to the A. So in terms of David's previous talk at the beginning of this session, sy to the S would be the tangent functor applied to S. So this would be an interface, this would be one of these tangenty things. And so the whole story is subsumed by, well, a lot of the story, but not the composition monoidal product, is subsumed by what he was talking about. So an initialized Moore machine also has this map from 1 to S, but that's really easy. It's just a map from the 1, 1 to SS, or a map of polynomials from Y to SY to the S. Okay, so I'm going to depict Moore machines. If the interface is AB, I'll depict it with this AB box, A on the left and B on the right. And if A happened to be a product and B happened to be a product, I could write them as many wires on the left and right. And so the box on top would be corresponding to the polynomial by to the A. The exponent is on the input side. And the one on the bottom is B1, B2, B3, the product, Y to the A1, A2. So here's a picture of a wiring diagram. It's got a controller, a plant, and a system. Looks a lot like Georgios' wiring diagram. He had a sensor also. And so the controller here is a polynomial of type by to the C. Now polynomial, you might think, oh, I don't care about polynomials. I like exponential things, or I like more complex things. I just want to note here, this polynomial is corresponding to a kind of data structure. It's telling you what the input type and output type are. B could be the set of strings or the set of real numbers or Rn. The plant also has arbitrary data flowing in and out, but we'll write it as a polynomial to keep track of that stuff. The output is C and the input is A times B. And the whole system here, which we could put into something even bigger as just one more little system, that would have type CY to the A. And so the wiring diagram itself represents a lens from controller, tensor, plant to system. You could write out what this is in terms of its set theoretic definition of what a morphism of polynomials is. And all it'll basically be is something that tells you that given data on the inside, we're going to project out the C, and we're going to transfer stuff all around. And so it's a very simple map. I think it includes like a projection and an isomorphism of sets. It's probably not clear, but it's quite easy to write this down as just a lens. So to summarize what we've said so far, a wiring diagram, or in this section of the talk, a wiring diagram is a lens, and each Moore machine is a lens. And so we can tensor the two Moore machines, sy to the S mapping to by to the C, and ty to the T mapping to cy to the AB, and get sty to the st mapping to this thing, this tensor product there, and then we could compose with the wiring diagram to get something on the outer box. So in other words, given a Moore machine on the inner box controller and a Moore machine on the filling in plant, we can get a Moore machine filling in system. And it's just all lenses through and through. Everything we've said is just lenses. And so we could replace all that stuff with, instead of just working with monomials, we could use polynomials. And we would see that a generalized Moore machine where we map to a polynomial instead of a monomial would allow us to have every state go to a different monomial here. So every state could go to a different interface. So in one state, where our eyes are open, and in another state, our eyes are closed. In one state, we're taking in, we're extending our hand to shake hands with somebody, and the other one, we're not extending our hand. And so the input-output type can change based on state. And then for wiring diagrams, it looks like this. So imagine you have a company, and based on its choice, it can either receive a widget from supplier 1 or supplier 2. And this whole picture up here is not two different pictures. It's one picture in the sense that it's exactly one map, one morphism in poly. This whole picture is one morphism in poly. The two suppliers have interface WY. They only are outputting. The company interface is 2y to the w. It's got two modes. We don't really consider them, they're kind of like output, but they're output to the system to decide who to connect to. And the outer box is a closed box to make things simple. So it's just y. It's got unchanging inputs and unchanging outputs. And so the whole picture represents a map from, this should be orange, wy, tensor 2 to the y, 2y to the w to y. And you can write out what that means, and it basically just comes down to a function of sets, 2w squared to w. And that will be, again, this should be orange. And that would be just evaluation. Okay, but the point here is that all of this, if we use polynomials instead of monomials, then we can get this mode-dependent wiring diagram stuff, where the company's internal state determines who it wires to. What made all this tick? What made that, remember that stream transducer stuff? Given a map sy to the s to p. What actually made that work was that sy to the s is a comonoid in poly. A comonoid is a polynomial with a map from k to k composed k, and a map from k to the unit, satisfying some usual laws. And if you were thinking about polynomial functors, poly in terms of functors from set to set, you'd call this a polynomial comonad instead of comonoid. And you would call sy to the s the store comonad if you're a Haskell person. So the way this works is that the functor from comonoids in poly to poly has a right adjoint. So if you take any comonoid in poly and look at the underlying polynomial, that operation has a right adjoint called cofree. And basically the formula for it is given by a limit. And that limit generalizes what people might know from coalgebra theory of the terminal coalgebra. So just to give an example of this kind of complicated looking thing up here, in the case where your polynomial p here is by to the a, then the cofree on p is b to the list a, y to the list a. So a lens from sy to the s to this thing would be a function from s times list a to b and s times list a to s, which would mean for any initial state s naught, you'd get a function that takes a list of a's and gives you a b. So a stream of a's or a list of a's would give you back an output, and a list of a's would give you a next state. And that's how we get our stream transducer. But the point is, what really made this work is comonoids. And my love affair with poly is really, to a large extent, about comonoids. Not only are they what make Moore machines tick, but Daniel Amann and Tarmo Ustalu proved that they're precisely categories. So comonoids in the category of poly are categories, full stop, or maybe comma, and the functors and the morphisms between comonoids are not functors, but cofunctors. These are what Bryce was talking about earlier today, cofunctors between categories. So the category of categories and cofunctors it does arise, as he said, as like categories with spans of discrete out vibrations and I think fully faithful or bijective on objects functors. I'm sorry, I've forgotten. But it's also just comonoids in poly. And the coalgebras on these comonoids correspond to the co-presheaves on these categories. And Richard Garner, I have one more slide, almost done. Richard Garner showed that bimodules between these guys correspond to parametric right adjoints between the co-presheave categories. So I've got exclamation points all over this slide because I just think it's such an exciting thing that's happening here. So all this stuff about about categories, co-presheaves, parametric right adjoints has a lot of relevance for data and data migration, but it's also just really neat to me from a theoretical perspective. So again, so to summarize, poly is exceptionally rich. It's got 4 monoidal structures. It's got 2 closures, both tensor and times are closed structures, closed monoidal structures. Comonoids are categories. Discrete left comodules are co-presheaves. Bimodules are parametric right adjoints. But it can also be used in functional programming for generalized lenses, in mode-dependent dynamical systems, and in databases and data migration. So I think it just provides a very expressive notation in calculus for thinking about dynamics and data. Thanks.
All right, thank you very much. Let's thank David silently. You can type in the chat or clap silently. Are there any questions? I have a question. In your example of mode-dependent dynamical systems, you said that this involves moving away from monomials, but I looked at this slide and all the polynomials I see are monomials.
That's true, right. That is true. So none of these, if you look at all these interfaces here, they're all exactly the same from one to the other. So the interfaces aren't changing here. And I think on this slide, right. So if we wanted to allow our interface to change, we could using polynomials, but we don't have to. What's happening here is that this 2 here it's as though it's 2 different monomials of type y to the w. Company here only has 1 input, but they're 2 different. You might think of these as 2 different interfaces, although I mean that's a bit strange. But this 2 is determining who it wires to.
Right.
Yeah, it's a bit of a shortcut explanation.
I see somebody has a hand up.
Yeah.
Zinovi?
It's me.
Hello.
Shoot.
Hello. Yeah, I'm Zinovi. Hi, everybody. Yeah, it's very nice and thought-provoking, and it seems it reminds something from linear logic. Did you think about it? Is there any relations, or it's just illusion? Because you have AND and OR for monoidal operations.
Yeah, I don't know. I mean, I know it's kind of a dialectica construction, but that's about as close as I get to knowing.
Valeria
can chime in.
Valeria.
Yeah. Hi, David.
Hi,
Yeah, very nice. Love it. Lovely. Kind of love to see databases kind of and dialectical in the same talk. But I was asking in the chat before, sorry, forgotten to put a video on. I was asking in the chat before, how connected is this to Tamara's stuff on her category of polynomials? And some, I had lots of answers on that, saying that this is just the version, the monomial version of it, just the one-to-one things. But it kind of, it's surprising to me that would be just the monomials, because, you know, one of the things that is interesting about Tamara's stuff is that it's connected to Joyal's by completion, right? So, you know, which there was a slide there where you had sigmas and pi's alternating. If you could, yeah, that one.
Yeah.
So you see that is the Joyal soft constraints thing, and or looks like it at least, which is completing a category under products and co-products alternating, kind of a little bit like you do with quantifiers and stuff. So I am a bit, I mean, I decided to then go and ask you directly the question. Do you know the connection between this and Tamara and Sean Moss's work?
No, I don't. In fact, maybe you could give me a reference after the.
I already put one in the chat.
Great,
I mean,
thank you.
I put Tamara's thesis, but after that, which is called a category of polynomials and type theory. So, you know, it says
Cool.
directly that's connected somehow.
Mm-hmm.
But I don't know, I don't know enough about that. So I don't know how much that stuff of hers connects to this very old André Joyal by completion.
Great,
Which I can put in the chat. I can send you in the chat to the reference as soon as I find it.
That would be very helpful. Thanks.
So, you know, it is all connected to linear logic. It's all connected to game semantics of linear logic, I think. Thank you.
All right.
Thanks.
I think we should be moving on. So if there are other questions, send them to the Zulip chat or another context. So let's all thank David, or one more time silently.